Rigid body. Anybody doesn't know what rigid body means. And by the way, this lecture has almost nothing to do with the previous lectures. If you studied no lectures at all, if you understood nothing from all the lectures before, that's perfectly fine to start fresh now. I'm telling you seriously. Because it's important. I was still not a long time ago, and sometimes I just skip it because I didn't study that class, and I know that this definitely will be in the class, and I have no idea. But this here, this lecture is not, okay? It's a new topic. You can start fresh if you like. Because if you made it thus far, so no need to drop anymore. You can start together now. Anybody doesn't understand the meaning of rigid body? No shame. Any question about that? Okay. Rigid body, like we discussed last time, it has translational degrees of freedom and rotational degrees of freedom. 6 degrees of freedom in the space. Okay? Anybody remembers from undergraduate what are the main branches of mechanics? What are the 2 main branches of mechanics? You can give it a shot. 2 main branches of mechanics. Our course, right? Yeah, sometimes statics and dynamics. Some other times we say dynamics and kinematics, right? Okay, what do we mean by these within the framework of rigid body? Well, dynamics is always concerned with getting you the acceleration. Dynamics is the meat. If A equals ma, given a force, I want the acceleration. So for a rigid body, mass time is the acceleration or rate of change of velocity of the center of mass. It's not any point, right? Equals the forces. I'm typically given the force and I want to get the velocity. So the dynamics, which is the meat, gives you the acceleration. That's perfectly fine. This is Newton's second law, right? So this is Newton. Whereas rotational degrees of freedom, that's perfectly fine. It's very similar, right? So I, maybe about the center of mass, times omega dot plus omega cross I omega, right? This is equal to the moment applied at the center of mass. Again, typically I'm given the moment, and I get from this equation, I get the angular acceleration. Okay? So here I get the linear acceleration, translational acceleration. Here I get the angular acceleration. What do we call this set of equations? Anybody remember? Euler, exactly. This is Euler equation for rigid body. Okay? So this is the meat, this is the dynamics. Given the forces or moments, you get the acceleration. Then, kinematics takes the output from the dynamics. The output is the acceleration, whether it is translational or rotational. Okay? And simply, using this acceleration, you integrate it forward to get complete description of the motion. Integrate the velocity once, to get the acceleration, once to get the velocity, correct? For both types of motion, to get the angular acceleration, to get the angular velocity. But then, to integrate the velocity to get the position, this is a little bit not trivial, at least for the angular motion. So, for here, if your velocity vector is represented in inertial frames, so that's fine, I can integrate it to get my position in the inertial frame. That's fine. But usually we write this equation in the body frame, so I need to get from the velocity from the body frame to velocity in the inertial frame in order to integrate. This equation should be in an inertial frame, otherwise it will not make sense. We'll talk about that later. But even though, if you have the velocity in the inertial frame and integrate it to get the position vector, that's fine here. What about here? This is the issue. what will you get if you integrate your angular velocity? You have three components, omega 1, omega 2, omega 3, in the body axis typically, because remember this equation is typically in the body axis. You have omega 1, omega 2, omega 3. If you integrate it, meaning you're adding omega 1 all over the time, you're adding omega 2 all over the time, or you're adding omega 3 all over the time, what you will get? It seems, at least from a unit, from a dimension perspective, I'll get a position-like quantity, right? That's right, but does it make sense or not? What is the position, what is the angular position that you will get? What's that? Because, remember, if you have a rigid body like this, assume that this is the x-axis, this is the y-axis, and this is the z-axis up, okay? Or it's down. So I'm doing rolling motion. So as I'm doing the rolling motion, you keep adding your angular velocity, you get the angle, right? Integrate your angular velocity, you get the angle, the roll angle. That's fine. But what if, while I'm doing rolling, I also did something else? So previously, my angular velocity was about this axis. This x-axis points to u. Eventually, my roll angular velocity is now about that axis. I cannot add these two omegas. They are not about the same axes, right? I cannot add them. I cannot keep adding omega times delta t and adding omega about another axis times delta t. I cannot do that. I have to bring them all back to the same frame of reference. So this thing, which looks trivial, integration of the angular velocity to get the angular position for a rigid body, this is a big deal, and we call it the rigid body kinematics. This is the topic of today and next lecture, 2 lectures. Rigid body kinematics, okay? Any question about that? Kinematics, okay, we got it. Any question? Please. Like I said, this has nothing, almost nothing to do with the previous lectures. If you understand, if you didn't understood anything, it's perfectly fine to start fresh. It's as if this is your first day.
Can you please go over this thing again? We have a problem that we have the angular velocity in
I have the angular velocity, and I want to know, I have the angular velocity as a function of time. Omega as a function of time, right?
on 3 different axes, right?
Yes. Omega 1 about the first body axis. This is a body axis, which means it's this axis, right? If the body rotates, it's going to rotate with the body. So eventually, I have my omega 1 about the axis points toward you. Then, after a while, I have omega 1 in the new time about this axis now. So, integration meaning you're adding this times delta t, right? You're adding these omegas. So you cannot add omega about that axis to omega about this axis, right? So, okay. Rigid body kinematics is that when you ask me what is dynamics, I'll tell you, okay, dynamics is a branch that studies the following. Given the forces, give you the acceleration. Okay? This is the dynamics. Rigid body kinematics is that given the angular velocity, omega, I want to see how the body attitude, the body angles in the space change with time. Okay? It's supposed to be simple, simply an integration, but this integration needs to make sense. Yes, Joseph, please?
So so you're saying the omega is given in the body frame?
Yes, this is typically the case. This equation is in the body frame. Because it doesn't make any sense if you... What is omega? Omega, at the beginning, is actually between 2 frames of reference. We have inertially fixed axes, and we have body axes. And omega is the angular velocity between the 2 sets of axes, actually, right? So, omega is represented in the body frame, intrinsically in the body frame, and this equation actually indeed is in the body frame. When we define h, the angular momentum equals I times omega, h is in the body frame, I in the body frame, omega is in the body frame. Okay?
But then we're interested in the angles in...
I want to know how, okay, so this rigid body is just moving and doing maneuvers in space. And I know the angular velocity. Simply you put gyros, 3 gyroscopes on the body, and you have complete information about your 3 omegas in the body axes, right? And using these omegas, angular velocity, I want to know the angular position, right? I want to know how this guy will make, its angle will change as it's maneuvering. The angles, how the angles will change, okay? Seems to be simply integration, but it's not. Because of this subtlety.
The integration is in body or in
The what?
the integration?
The integration is not, I mean, we cannot say integration is in the body frame or outside of the body frame. You integrate a quantity, you integrate the quantity. Simply you adding this quantity all over the time. You keep accumulating it. So this is why we're saying, I cannot simply integrate this guy to get something meaningful. The integration sign will not ask you whether you're doing it in the body frame or not. You will do the calculus. But what you get out of that, is it meaningful or not? This is the thing. And this is the whole topic of rigid body kinematics. So simply, like I said, we have actually 3 sets of axes here. N1 inertial frame, N2, N3. And I have 3 body axes, in general, arbitrary given. Body axes. So this is one, B1, maybe B2 to the board or something like this, and B3 completing the trail. So this is supposed to be a 3-dimensional schematic. I want to write B1, each axis, I want to write each axis with respect to the inertial frame, right? So B1, for example, is equal to, well, any axis is defined by its direction cosines. So this B1, I want to write it in the N frame, 1, 2, 3, the black one. Well, if I know these angles, I'm done. Alpha 1, 1, I will call this alpha 1, 2, according to the book notation. And this guy is alpha 1, 3. The 3 angles that the first body axis makes with the 3 inertial axes. And simply, if I have these 3 angles, I can write this guy B1 in terms of N1, N2, N3. What's that? This is simply cosines of these 3 angles. So cosine alpha 1, 1, and you know I like to write the cosine as just C, alpha 1, 2, cosine alpha 1, 3. N1, N2, N3 are unit vectors, and the same for B1, B2, B3. Okay? Any question about this equation? Any question? You have any question about this equation? Yes, Sanjay.
What's the positive orientation for the angle? Or
No, it's from the inertial to the axis.
oh, okay.
And it doesn't matter much because we're relying on cosines, because cosine negative the angle is the same as the angle. Any questions? Yeah. Okay, so let's define B2. Well, it has other 3 angles from N1, N2, N3. So this is alpha 2, 1. This is alpha 2, 2. And this guy is alpha 2, 3. And I need the 3 cosines here. Alpha 2, 1, alpha 2, 2, alpha 2, 3. And if you do the same, you will get cosine alpha 3, 1, and so on. Okay? Any question, please? So 9 angles. 9 angles. If we know these 9 angles, at any time, So given the angular velocity vector, I know the angular velocity. Do you want to know the angular position? Well, the angular position is simply described by these 9 angles. If I have these 9 angles, at any moment of time, I will completely characterize these B's on the body axes, okay? Of course, I don't need the whole set of 9 angles because they are related to each other, right? Can you give me any relation between the first row components? Well, these are the components of B1 in the N frame, right? And what is the length of B1? It's unit. So this square plus this square plus this square equals 1. So you have one equation for each row, and we'll see that we have also one equation for each column. We call this the rotation matrix, R, that describes the body frame with respect to the inertial frame. And it has 9 components. It's not symmetric. It's not symmetric. Okay? Simply, and you can see very easily, this angle is totally different from that angle. Well, so this is the body, B1, B2, B3. In terms of inertia, I could have done the exact same thing the other way around, which is I will now write N1, N2, N3 with respect to B1, B2, B3. I can do the same, exactly. I can write N1 with respect to the B's. I just need the angles. What you need here is cosine the angle between 1 and 1. This is simply cosine alpha 1, 1. Here is cosine the angle between N1 and B2. Well, I have it from there. Cosine the angle between N1 and B2, it's here, right? So this is cosine alpha to 1, correct? What's this guy? I'll give you some time to write. What's this guy? Cosine alpha 3, 1. What is this row?
The column of the other.
Exactly, it's the first column. So you can simply see that the relation between N and B, this matrix will be what?
Transpose.
R transpose. Okay? Any question about that? Summarizing these two relations is that the body frame is simply a rotation matrix times the end frame, and vice versa, the end frame is simply R transpose times the body frame. If you have one, you get the other, and this is obviously seen, which means that, what does it imply? It implies that R inverse is the transpose, equivalently R times R transpose is the identity matrix. Correct? Which means it's an orthogonal matrix. This is the definition of an orthogonal matrix. Okay? So 9 components subject to 6 constraints. What are these 6 constraints?